especially true in Mediterranean climates where they replenish critical water supply. And the converse of that is true. If we have too few of the atmospheric rivers, then you have drought, and then if you have too many, you have flooding. So there's a lot of still questions and scientific understanding that needs to be done with atmospheric rivers. But today we have several panelists on here, both on the science side and on the public side, who have worked very hard to understand atmospheric rivers from the scientific side, then make that connection to an understanding of how this impacts society and things that can be done as a result of better understanding. So today we have 3 panelists, 2 of whom are in the room and 1 is online. So our first will be Marty Ralph, who's the director of the Center for Water. Western, there we go. He'll tell you when he gets up here. I can never remember what the 3 W's are. There's Western, Water, and Weather in there. Right. At Scripps Institution of Oceanography, Marty spent 20 years or so at NOAA as a program manager, and then came to Scripps to start this center because of his strong interest in making these connections. We'll then be followed with a virtual presentation by Irina Gorodetskaya, who is in Portugal today and with us online. And lastly then Brad Sherwood, who's the Assistant General Manager at Sonoma Water Agency, will be talking about how they are making use of and partnering with the work that's being done on the scientific side. So I'm going to turn it over now to our first speaker, which will be Marty.
Thank you so much, Carol Ann, and thank you so much, Carol Ann, and thank you for joining, and thank you, Brad and Irina, for being on our panel. Let me jump right in here. What I'll be doing in this part of the briefing is really trying to make a connection between, explain the connections between the oceans and atmospheric rivers, and then we'll hear from Irina about the role of atmospheric rivers in Antarctic climate, including ice mass balance and the implications for sea level rise, which are pretty profound. And then finally we'll hear from Brad Sherwood, who's a water manager, about how they're using forecast information on atmospheric rivers to help manage water. All righty. Okay. Is this better? All right. 1 inch matters. Okay, got it. So what is an atmospheric river? Well, just like the name says, it's a river in the sky, but it's a river of water vapor instead of liquid on land. But if you slice across one of these, and this is a schematic from a Scientific American article about 10 years ago, showing it as a ribbon of water vapor transport hitting the coast and causing rain and snow. If you slice across an atmospheric river, an average one, it's transporting more than double the Amazon River worth of water, but it's doing it as vapor instead of liquid. On average, there's only 3 or 4 of these around the northern hemisphere at any one time, and they are transporting in combination 90 to 95% of the water vapor transport horizontally is happening in these few atmospheric rivers. So because they're so effective at transporting water, when they reach the shore or get lifted up, they produce a lot of precipitation. And that can lead to both flooding, but also very beneficial water supply. In a place like California or parts of the Iberian Peninsula or many other western coastal areas around the world, they can contribute up to 50% of the annual precipitation in just a few storms each year. And in California, for example, whether we slide into drought or go into flood hinges entirely, almost entirely, on atmospheric rivers each year. So they are the make or break thing for both water supply and flood. All right, well, what is the connection to the ocean here? Well, intuitively, I'm sure we can all envision that most of the water vapor that an atmospheric river carries comes from the ocean through evaporation. And I'm showing a picture here in the upper left of an atmospheric river in water vapor, and you can see how narrow and long it is. And then at the bottom, you can see the trajectories from where the air in the atmospheric river came from. And those red ones are showing that it comes from the warm side of the AR a bit, and that's where the water vapor is getting evaporated into that air and then flowing into the AR, and then that becomes what is transported and ultimately becomes precipitation. So how does the ocean influence all this? Well, first of all, the broad, sort of global SST patterns or basin-wide patterns influence the storm track, which influences where the atmospheric rivers are. And then also, of course, there's the fact that when you have a warmer SST, you can evaporate more water vapor into the air. So if you have a warm SST anomaly, you can end up strengthening the AR by adding water vapor. And then in addition, very interestingly, the fact is that it's that evaporation that really does fuel the ARs. I'll add just one last bit here, is that the ARs also impact the ocean. And that's one of the emerging areas of interest. And salinity, because a lot of rain falls from the ARs on the ocean, stratification of the ocean boundary layer, nutrient availability, and other factors in the ocean are influenced by the ARs that are going overhead. One of the new areas we're working on is how when an atmospheric river is moving all that moist air, it tends to be moving it from warmer areas to colder over the ocean. And these trajectories right here show how we're basically on average in these cases bringing the air in the atmospheric river in 24 hours ends up over water that's like 8 degrees Celsius cooler than where it started. And what that means is it's losing water vapor, it's losing heat to the ocean surface. And what that does is it creates a stable boundary layer. That stable boundary layer sort of decouples the atmospheric river, which now is a little bit aloft by a few hundred meters, from the ocean itself, which has huge implications for evaporation and for prediction. And that graph in the middle shows the black lines are the AR, essentially, contours of the vapor transport, and the colors are the amount of downward sensible heat flux. They're perfectly aligned, essentially. So these ARs are really driving heat into the ocean, and the ocean is cooling the atmosphere below the AR. Another thing ARs are responsible for is a lot of the hazards in the western U.S. Associated with water come because we get heavy rains in areas that can cause debris flows, and sadly this can take a lot of lives. But with good warnings, those people can be evacuated, especially since there are burn areas that otherwise might produce these debris flows. And in this storm, for example, this one became a $1 billion weather disaster because the storm was strong enough to do all this damage. But it also, there were no fatalities because we had warnings that our work has helped enable that were accurate enough with the National Weather Service to issue that led to evacuations of people who were in harm's way otherwise. And a storm like this in decades past would likely have produced quite a number of fatalities. I'm going to probably accelerate here a little bit. One thing we did was create an atmospheric river scale, and this goes from 1 to 5. And it depends on the duration of the AR and on the strength of it. So unlike the hurricane scale, which is all about the wind maximum, but in the case of Hurricane Harvey or Florence, the big thing about the hurricanes in those cases is they stalled over those cities, and that created catastrophic rainfall. We have factored in the stalling effect through factoring in the duration of the AR. I won't explain this for sake of time, but it's being used a fair bit now. And then we did a study with an economist, Tom Corringham, that showed the ranking of the AR on the AR scale basically correlates logarithmically with the median damages that occur, with the weaker ARs largely being beneficial and the stronger ones being mostly hazardous, and on average a couple $300 million of damage for a typical AR5, and we've seen those now recently. The interest in this led to the creation of a common language paper in Scientific American published just 2 months ago. And I would invite you to take a look at that if you're not in meteorology or hydrology. It's written in a way that tells the story of science to the solutions that we're striving for, that you'll hear more about from Brad Sherwood as well on the water management side. In addition, the topic, which was really pretty quiet for a few years, really got back into the area of scientific and policy attention about 10 years ago. And the National Climate Assessment for the U.S., the fourth one, added atmospheric rivers as a new category of extreme storms to track from a climate change perspective. We've also written a book on ARs. There are, I think, each year now on average about 100 scientific publications on atmospheric rivers from around the world. It's become a significant topic of interest to many individuals. In addition, climate change is setting the stage for even stronger ARs. And I'll jump ahead to this part of it here, that basically the graph there on the right shows that we have an increase in the amount of rainfall on the wettest, like couple percent of days each year in California, and many more dry days in between. So essentially we'll probably end up with the same amount of annual precipitation, but more of it will occur in a few big events each year, and there'll be longer dry spells in between. That has a lot of policy implications for water management and flood control that you can imagine. Additionally, Tom Corningham again led a study of the impacts with climate change, and what we see is, looking out to 2100 roughly, that we project a doubling or a tripling of the damages. And if we go to RCP 4.5, instead of a tripling, the projection is it'll be a doubling of damages. And finally, I want to show just a couple last slides here of introducing Irina Groditskaya's topic, which is about Antarctic ARs. And this is a case in the lower right diagram there. You see an anomaly in the surface temperature at Dome C, a very cold place on the top of the Antarctic ice cap, that had a 77-degree Fahrenheit warm anomaly on one day. They had their high temperature for any day of the year in the late fall season. And that turned out to be associated with an atmospheric river, which we see on the left here, hit that region of Antarctica. And it turned out that was a storm that was stronger than any in the 40 years of data that we have to analyze, than any AR that had ever hit that region by like 70%. So this was a real outlier storm, and it's the kind of thing that climate change is predicting we'll see more extremes of, and we'll hear more from Irina about what this might mean. Finally, I just want to share that when we don't have enough ARs, those arrows are where ARs hit the coast in water year 2018 or 19, and then in 2022, and the color fill over land is the amount of precipitation. You can see how dry it was in California where we had an absence of ARs. Finally, the last slide here is going to be setting up for Brad Sherwood to share about how information on ARs can be useful in reservoir operations. There's a lot of work to be done to study this specifically for each reservoir, but in the case of the pilot study we did in their backyard, we discovered that we could, and as you can see the graph here, save essentially 20% more water going into the dry season in the third driest year on record in that watershed. And with that, I would like to go ahead and turn it over to, oh, there's my closing thing there. We'll skip that. And shift over to Irina Groditskaya. Do you want to make the transition help a little bit? Okay. So let's go ahead, and I'm not sure about the process of transferring. I won't touch anything. Irina, you have the floor.
Thank you very much, Marty.
Irina, this is Carol Ann. So just when you're ready for me to move ahead on a slide, just say next.
The problem is that I don't see all the slides as you see them in the audience.
She sees one.
Is it okay for you that I share my screen with my slides, because I don't see the screen? Okay. Oh, that's perfect. Okay.
Can you see your slides now?
Yes, it's not the same. I think things have been moved, but try. Can you please put them in the presentation mode?
Okay. Are you able to use these slides?
I cannot see the slides.
Okay, so these are the slides that we have. Are you able to use these slides?
Okay, I can see the slides now. Can you please go in the presentation mode? And I hope that the slides are okay because the first slide is really displaced. Can you please go in the presentation mode?
Yes, but we can't do that while we're chatting with her. So we have to wait till we're not chatting, and then we can do that. All right. So he wants us to do that. But we can't do that while we're chatting. All right. Can you see your slides now? She can't hear us.
Can you please, I'm okay to use my slides, but can you please put me in the presentation mode, my slides? They are not in the presentation mode now. Okay. I am okay with using the slides as were shown on the screen, but they were not in the presentation mode. So if you can please try again with my presentation that you have.
You guys.
Okay, I'm the host now. Okay. Can you see my slides now? Okay, is this okay? Can I go ahead?
She cannot hear us. That's part of the issue, is that we're having to chat with her, so she cannot hear us. Just in case you're wondering why it seems like we're being extra obtuse in how we're doing everything.
Okay, I will go ahead. Marcy, can you please give me a thumb up that I can go ahead? I can see you, but I cannot hear anybody. Okay, perfect. Thank you very much. And sorry about these technical issues. I hope you can see my slides well now, because I could not see anything that was happening on the screen. So thanks for letting me to share the slides here. So my name is Irina Gradetska, and I'm speaking to you from Portugal, where I'm working as a senior researcher. And I have been also a lead author in the recent IPCC report. And in my presentation, I will be touching on several important aspects of a topic about Antarctica and atmospheric rivers, and what are the implications for sea level rise. So one of the key conclusions from the recent IPCC report, Working Group 1, was that many changes due to past and future greenhouse gas emissions are irreversible. That means that they will continue for centuries to millennia, and especially this concerns changes in the ocean ice sheets and global sea level. So what we have known from observations is that from the beginning of 20th century, the global sea level has risen by 20 centimeters. And what is also alarming to know is that over the last several decades, so from 1990 to 2020, so the rate of change of global sea level, that is how much it changes per year, has doubled compared to the mean sea level rate change over the 20th century. So what is happening, and what are the main contributors to sea level rise? So first of all, we know that it's the ocean thermal expansion, of course, and it has been a major contributor prior to 2006. However, since 2006, glaciers and Greenland and Antarctic ice sheet melting has been the dominant contributor to sea level rise. So there are some processes, there has been a shift in processes which we have to understand if you want to understand the future sea level rise, which by the different scenario emissions and the most aggressive emission, if you don't change anything in the way we live now, sea level rise is projected to increase by 1 meter or even higher by 2100. And what we know is that Antarctic and Greenland and mountain glaciers will play really a key role in this global sea level increase. So in the future, we know from different scenarios that, first of all, we see that there is a huge spread between the scenarios. But what we see also is that there is a definite answer that the sea level rise will continue despite, even if we decrease the emissions. But what really matters is that every degree and every scenario and every choice counts, because we have a choice of the world with a increase of sea level rise from half a meter or even higher. And you see this really alarming dashed lines and dotted lines, which I will not go in details, but what I can tell you is that the instability of Antarctic ice sheet plays really an important role in determining how much the sea level rise will increase, and also how drastic and how fast and how unpredictable it can be. So what is happening with Antarctica? As you can see from this plot, which is coming from the satellite observations, GRACE observations, that Antarctica has been losing mass. So the mean average mass loss per year is 149 gigatons, which is a huge number. Also, you can see that here the slide is past the 2006, when, as I mentioned earlier, the rate of change of sea level rise, and here we can see the rate of change of Antarctic mass loss has increased. What we can see also that it's not homogeneous. We can see a huge increase in the sea level in the Antarctic mass loss. So really the melt happening over West Antarctica. So this is shown by the dark red colors. And here we see that West Antarctica, huge part of it, and also Antarctic Peninsula, really affected by the melting of the ice sheet. However, we can see also these blue areas, which indicate where the mass balance has increased. So we can see that there is heterogeneity, but again, these spatial patterns, they do not change the overall picture, which is shown in this time series again, that Antarctica has been losing mass and adding a lot of water to the oceans. What is happening in Antarctica? Just a quick recap. So what is it when we talk about the total mass change of Antarctica? We talk about the surface mass balance and the dynamic discharge. And in this presentation, we'll be concerned only about the surface mass balance, which is the main component of the surface mass balance. The input comes from precipitation, and then the melt is runoff, and then we also lose mass by sublimation, evaporation, and blowing snow erosion. So when we talk about runoff, this is the surface melt and rainfall, and then insignificant contribution of other components. So here on the figures, you can see and compare how much precipitation falls on Antarctica and how much of surface melt actually it experiences. So we can see that precipitation is really high along the coast, especially over the West Antarctic ice sheet, and it's really dry, and it's a desert in the interior, while the surface melt concerns mostly the ice shelves, so the coastal zones along the Antarctic coast and the major ice shelves. And we can see that we really have the largest melt occurring over the Larsen Sea ice shelf in the eastern Antarctic Peninsula. So what do atmospheric rivers have to do with these changes? Atmospheric rivers have contrasting impacts on Antarctic surface mass balance. And here I'm showing you the key impacts. So first of all, in the left column, you can see the extreme snowfall is one of the key impacts from atmospheric rivers. So atmospheric rivers can cause 60 to 80% of extreme snowfall in the coastal and escarpment Antarctic regions. This you can see on the figure, which shows, so the colors, the darker blue shows that up to 80% in these dark blue areas, this is the extreme precipitation, what in statistical language we call the 99th percentile. So the tail, the most anomalous snowfall events are actually connected to atmospheric rivers. However, in the central column, we can see a totally opposite effect that atmospheric rivers can have on Antarctica. So they can actually cause major surface melt events. And here on the top, you can see the simulation of surface melt by regional climate model called MAR in summer. And the colors indicate now the melt magnitude percentage explained by ARs. So you can compare the precipitation magnitude percentage on the left, and here this is the melt magnitude percentage only in West Antarctica. And we can see in summer the darkest red color, so this is 80, even 100% of the major melt events in summer are actually related to atmospheric rivers. And in winter, we can see that much smaller area is affected by the melt events, but it's really important because these are the ice shelves, which are really supporting the glaciers. When the ice shelves are retreating, the glaciers accelerate and the mass loss from Antarctica accelerates. So these are really key regions, and we see that atmospheric rivers are really key in causing melt over the Antarctic Peninsula and its ice shelves. Another key component is rainfall, which people don't really talk much about when they talk about Antarctica, but we know that as in the Arctic, in the future, rainfall frequency is projected to increase. And actually, atmospheric rivers will bring also rainfall to the coastal Antarctica. And here we show that the number of rainy days, it's yet the study it's really in investigation. Here I'm not showing the percentage of contribution of atmospheric rivers, but only the amount of rainy days. And we see that over the Antarctic Peninsula, they really have high frequency, and the atmospheric rivers definitely play an important role here. Atmospheric rivers have contrasting impacts, and here I'm showing you these two specific studies, two specific cases of atmospheric rivers. One on the left is bringing extreme snowfall event, and one on the right that brought major melt event to Antarctica. So the atmospheric river on the left that reached Antarctic, so East Antarctica in February 2011, it brought actually more than a quarter of total annual regional precipitation. Of total annual. This is really a huge number. And actually, there were several intense atmospheric rivers that happened during this year. It was really an anomalous year. And they added up to a total of 160 gigaton of mass. Again, that's a huge amount, right? When you look on the right, again, really intense atmospheric river. And here I'm using the atmospheric river scale category that Marty has introduced in his talk. So we see that it's really intense atmospheric river hits in South and South America, so AR scale 5. Then it continues to Antarctic Peninsula, and then it was AR scale 3. These events are really rare, but they are so intense and their impacts are huge. However, in this event, while we had really a lot of moisture reaching Antarctica, the impact was not the extreme snowfall as in the event on the left, which also happened during summer, but we had a heat wave, record high temperatures, rainfall, and a massive surface melt event. And it happened just this February 2022. So when we talk about the contrasting impacts of atmospheric rivers, we have to remember also that they actually have a lot of common things. And what is common is their source regions of moisture and heat where they're actually coming from. And this is the ocean. So we're actually talking about a really long-range transport of heat and moisture. And here what is happening in subtropical, and also I can tell the tropical ocean, because the dynamics really depends on the tropical large-scale circulation, which I will not have time to go into details. But here, look at this back trajectory. So this is another way that we look in the atmospheric rivers. We call it Lagrangian perspective. So we can trace back the air parcels that caused either heat wave, that is on the right, or precipitation, extreme precipitation, that is the figure on the left. So we track them back 10 days, and then we found out with specific analysis that the atmospheric river that brought the extreme precipitation to East Antarctica, that is shown on the left, it took its moisture from the subtropical Atlantic Ocean. While the atmospheric river bringing the heat wave to Antarctic Peninsula in February took its moisture and heat from subtropical Pacific Ocean. So this is this region. And then it rapidly advanced to Antarctic Peninsula. So this is the really link between the atmospheric rivers and the ocean, the first order link, that they actually take their moisture from the ocean and then they go over a much colder ocean when they bring the moisture and heat to Antarctica. And then they add mass, or they can actually decrease the mass in Antarctica. So it's really a key role in the water cycle. So here on the left, we can see these impacts. So these short events, but they can have really strong impacts. So we see these two anomalous years. So 2009 and 2011, each of this year actually added up to 160 gigaton of mass, and just regionally. So overall, it compensated for the Antarctic mass loss, but the Antarctic mass loss still continues. So these events, while adding mass, they do not reverse the loss of mass from Antarctica. And on the right, you can see another impact, huge impact of atmospheric river, which actually belongs to one of these irreversible impacts. Because the atmospheric river, which happened here in January 2008, it disintegrated and fragmented the landfast ice in the Larsen A and B embayments, and it generated 7.2 gigaton of meltwater, triggering calving of Larsen B ice shelf remnants, which was about 11 kilometers long in that area, and that led to accelerated glacier retreats from Antarctic Peninsula. So you can see these two completely contrasting impacts of atmospheric rivers. So now I would like to talk about this mega atmospheric river event that Marty has already mentioned, when it was really an extraordinary increase of temperature in East Antarctica, and it happened again this year in March 2022. And I will not go in details, as Marty has already introduced this event, but I would like to talk about this contrasting impacts, which now are combined in just one atmospheric river event. So here on the left, you can see a photograph of a lot of fresh snow, which I can tell you is not a usual image at Dawn's Peak to have so much fresh snow. Usually it receives less than 1 centimeter per year. Now in one event, it received more than 10 centimeters. And it was caused by an atmospheric river bringing enormous amount of moisture and heat. And what happened, Antarctic ice sheet gained up to 300 gigaton of mass just in one month, in March 2022. So while causing a heat wave, an increase in temperature, it actually caused enormous amount of snowfall that fell on this area in Antarctica. However, this impact of the atmospheric river didn't stop there. And what happened also during this event, there was a lot of melt and rainfall along the coast. And another important event that was all over the news is that already weakened Conger ice shelf collapsed during the atmospheric river event. So it was already weakened, and atmospheric river destabilized, and there were other important processes happening, and there is a lot of investigation happening on right now. But what we can say for sure is that atmospheric rivers are really important players in Antarctic surface mass balance and in sea level rise. And they have contrasting impacts. So they cause snowfall extremes in Antarctica, and they can compensate for Antarctic mass loss, and by this somehow compensate, so reduce the sea level rise. They also bring heat waves and melt and rainfall, and by this they can further destabilize ice shelves and accelerate glacier retreat, contributing to sea level rise. And the question is, what is going to happen in the future? So we know that increasing risk of Antarctic ice sheet instability in a warming climate. So now we can say they also depend on atmospheric rivers and moisture and heat transport. And every degree of global warming matters. And I can add here also that every atmospheric river counts. So thank you very much for your attention, and I will be happy to answer your questions.
I apologize. I do not have any slides. I will be talking to you like this, and I use my hands a lot. My name is Brad Sherwood. I'm the Assistant General Manager of the Sonoma County Water Agency. That's in California. It's about an hour north of San Francisco. It's where the best wine in the world is produced. I know, I thought, yeah. We also provide some of the highest quality drinking water to over 600,000 residents in the northern San Francisco Bay Area. So we are a public utility. We are funded by the sale of drinking water to 9 cities and water districts. Mayor Elward is with us today. She's the mayor of Rohnert Park, one of our main water contractors. We are here today, and we came to COP27 because of the work that's being produced by Scripps, the Center for Western Weather and Water Extremes, at the helm of Dr. Marty Ralph. Let me tell you two figures. If you walk out of here for my talk, remember these two things. Forecast-informed reservoir operations. Forecast-informed reservoir operations is a new, flexible way we as water managers can better operate our reservoirs without spending millions of dollars of infrastructure improvements. Right now, we are implementing the work you just heard Marty talk about at Lake Mendocino, one of our 2 drinking water reservoirs. Lake Mendocino literally relies on atmospheric rivers to fill up on an annual basis to provide farms and communities with their drinking water. Lake Mendocino is also a major flood protection facility for over 1 million people throughout the Mendocino and Sonoma Counties regions. So you can see where I'm going here. Lake Mendocino, atmospheric rivers, really tight, close relationship. But before we engaged with Dr. Ralph and his team at CW3E, we did not understand what an AR, or atmospheric river, was or how it impacted our region. After nearly a decade of research, we have found out through his work, 50+% of our water comes from atmospheric rivers. How can we better manage our reservoirs knowing when these AR events are going to happen and how much water they're going to produce for our reservoirs? Well, here's the short answer. By using advanced AR forecasting research, soil probes in the ground, stream meters, you name it, a full suite of new tools and technology being implemented in Lake Mendocino, we were able to save 20% of that reservoir's water supply in the midst of a major drought. 20% may not seem like a lot, but for 22,500 households who rely on that 20% for their water, just saving enough water for one household is priceless. That is the result that we're seeing at Lake Mendocino right now by implementing forecast-informed reservoir operations. It's not an easy process, right? 10 years of working with the U.S. Army Corps of Engineers, a suite of federal and state environmental agencies. But what we were able to do with CW3E was develop and study the paperwork and the research needed to back up a viability study that showed the U.S. Army Corps of Engineers, and if I don't know, are there any Army Corps of Engineers folks here in the room? Great agency, great partners, but it's a long process to get a change, right, through any federal agency. And the beautiful thing about it is the Army Corps of Engineers took the work by CW3E and literally changed what's called a water control manual. It's literally a binder this thick that was written before the fax machine was even invented. And that is how they used to manage water supply and flood control at Lake Mendocino. This new technology, this new AR research has allowed the Army Corps and Sonoma Water to rewrite the manual step by step. It allows for more flexibility. We now know on certainty when an atmospheric river is coming to Lake Mendocino. We now know in a time scale of 1 to 7 days where and how much water that atmospheric river is going to deliver. That means we can either release more water from that reservoir to protect communities downstream from flooding, or that means we are not going to release water when we know the reservoir can take all that AR water for future use. Case in point. 2012, we had a massive atmospheric river come and literally fill Lake Mendocino up. It went up and over the flood control pool. Think of the two pools of a reservoir like a cake. You got the water, drinking water pool for the reservoir, and then you got the flood control pool, and then you got the dam top, right? And this whole curve and this water control manual essentially tells the Army Corps and Sonoma Water when they can release water based on how much water is in each pool. Bottom line is we now have more flexibility with that curve and that pool. So in 2012, we didn't have this technology for AR. We were still kind of working on well, we hadn't even developed a concept yet. The Army Corps, not having this new technology, released thousands of gallons of water from Lake Mendocino. And guess what? Had we had the AR research and weather forecasting we have today, we would have known in 2012 that we were just beginning a major drought. And there were no ARs or rain coming in the next week, in the next 2 weeks, in the next month. As a matter of fact, we didn't get an AR for another year and a half. So they unnecessarily, based on the pre-fax machine water control manual, released this water when they should have held it. We should have held it. We shouldn't have released it because we could have literally saved that water for use for farms and urban water users. Fast forward, remember that 20% I was talking about? Well, that 20% was the water that we saved because of the CW3E FIRA work. So we corrected our policies at the local level by working with the university, CW3E, and we even changed federal policy. So here's the big picture. Here we are at COP, and that's why we're at COP. A little water agency in Sonoma County flew all the way to Egypt because we want to be able to share with the world there are better ways to manage our reservoirs. There are better ways to manage our water, and it's with advanced forecasting and weather prediction services, which CW3E provides. And if we can get one other water agency, which, by the way, many are starting to replicate this work throughout California and the world under Marty's leadership, let's get one other water agency to save another 20% of water. Just imagine what that could do worldwide. And it's all because local government is partnering with universities, our federal and state partners, right? And guess what? At the end of the day, our local leaders, like our mayor here, she has to answer to her ratepayers as to why we raise rates, why we have water, why don't we have water, how are we responding to droughts and extreme weather. This is an answer for future concerns on climate change and how we're adapting. So from Little Sonoma County, we want you to enjoy our worldwide famous wine and also come to town and enjoy our tap water that is FIRO produced. So that is the end of my talk. Forecast-informed reservoir operations. I just ask you to remember that. Google it when you get home or right now on your phones and bookmark it, because it really is a fantastic partnership, an example to what COP27 should be doing and asking every government to implement. So thank you.
Thank you to all of our panelists. We're going to open it up for questions in just a moment, but while you're thinking about the questions you'd like to ask, I just find this example of the combination of, the forecasters and the public utilities working together to be just the most inspiring story. And I'll just have one question for you. Who started that partnership? Who reached out first and asked that question?
a public utilities staffer, we answer to a local board of supervisors, local elected officials who represent our ratepayers. So when the Army Corps of Engineers released that water in 2012, we had to answer to our local policyholders and makers and they were asking us, how could you let this happen? Why did you let the Army Corps release that water? And that made us as staff look internally at our processes, hence the relationship developed with Marty Ralph and CW3E. So from our vantage point, it very much is about listening to our local elected officials, our board of directors. Bottom line, it's our community. Had our community not wanted this, we wouldn't be doing it. But the community wouldn't have known about this had we not reached out to Marty and developed the policy solution. So from our point, it's community driven, and your local public policymakers, your mayors play a huge role in working with their utility staff to help get policies moving.
Thank you. Yeah, so there's a number of keys there. There was the reaching out on the science side with a concept of what you thought could be done. The recognition that there's a lot we can do at the local level. Very often we forget, I think, that there's that work that can be done in our towns, in our cities, and our counties that can actually move the needle on doing things. And I think that's a really inspiring story. So I'm going to open it up now for questions here. Dr. Gorodyetskaya cannot hear us, but we are going to chat the questions to her so she can also answer questions.
Marty, since you're asking a question, I've been, sitting next to you for quite a few days. Now that you make a presentation, where else around the world, around the globe, do you find out this river? And are there a possibility of using the research to help any part of the world, and particularly in tropical and subtropical areas, where they have not as long as drought and potential drought because the glaciers are melting and they need water.
Yeah, thank you very much for the question. Atmospheric rivers are really primarily focused in the mid-latitudes and subtropics and the polar regions. Tropical areas are a bit different meteorologically. The west coast of continents is an area that's especially subtropical climates like the Mediterranean climates are really prone to droughts that result from an absence of ARs in that area. From year to year, that can change a lot. Those areas, I do believe there's potential to use this knowledge to apply it to water management in ways that factor in that forecasting and help people keep water after a storm, knowing no storm is coming in the next few days. They can risk holding it another day. And then if a forecast is, there's a big storm coming, they have time to release that extra water safely. I believe that could translate to a major increase in water supply reliability in significant regions of the world, like Chile, Western Australia, New Zealand, the Indian subcontinent, including the Himalayas, Western Europe, Western U.S. There's a lot of parts of the world where this could be really key. The question was speaking about the data we're using to help with the forecasting. I didn't have time to share, but there's a whole set of things we're doing. In weather forecasting, one of the challenges is having observations to start the forecast model every day. And over the oceans, where these ARs typically form, we don't have as much of that traditional data that we have over land. So I started a program with colleagues in the National Weather Service and the Air Force, U.S. Air Force, to fly out into the ARs over the Pacific, sample them with drop-ons, we call them, little parachutes, like Coke can size sensor, temperature, pressure, wind, water vapor, radios it back to the aircraft sends it by satellite to a big data bucket. That then is the data bucket that all the global models use to initialize their forecasts. We've now shown, including many colleagues in other agencies, that these data are making the forecasts better in the Northern Hemisphere, and in particular the AR forecasts on the West Coast. That's one of the linchpins. The other is a weather prediction model that we've developed at our center that is tailored to predicting atmospheric rivers on the West Coast better than any place else. And when you develop a weather model, you got to decide what is it you're trying to predict best. Is it hurricanes? Is it convection? Is it clouds? Is it polar weather? You get different models depending on different versions of a model depending on what your priority is. Those are two of our main efforts. We're also doing machine learning, artificial intelligence, ocean science, a variety of things.
Just a small comment also. Yeah, thank you for this question about the data, the data models in the polar regions. One of the aspects about atmospheric rivers is they're really difficult to measure, and not only in California, but there are bad weather events, right? So we really have this problem, especially in the polar regions. And we use a lot of autonomous systems and more. So we have also satellites, and we work on the improvement of the satellite, deriving the observations from satellite. And we also have a special approach called the targeted observing periods. And there is a year of polar prediction, which has been doing these measurements both in the Arctic and Antarctic, and very successful. So we have a lot of observations where international collaboration is really key, because people from all over the world, they join their resources to target one specific event of atmospheric river in Antarctic or in the Arctic. And it has given enormous unprecedented data and unique opportunities to have this data together with the models modelers are targeting their high resolution model simulations only for these specific events. Again, so it's difficult to measure, and we find the ways to do it via really strong international collaboration and combining resources. So I would like to highlight this, that this brings also a lot of people and scientists around the world together.
I had never heard about atmospheric river, so thanks. It's a great experience. I hear that if it's managed properly, it can have some very positive impact on the way we manage water, and then it has some negative or some more risky impact, for example, in Antarctica. With climate change, do you see the phenomenon of atmospheric rivers increasing both in terms of intensity and occurrence? Or is this like a cycle that you predict is going to increase?
The question was about climate change and atmospheric rivers. The key thing, the fuel of an atmospheric river is water vapor, and it's pushed along by the wind. So those two parameters, whatever's going to change those two parameters will influence ARs in the future. The most profound influence we've studied, there's a nice paper by Labors et al. It shows the wind change is sort of small, but as the atmosphere warms, it can hold more water vapor. So basically a warmer atmosphere can add fuel to the ARs. And there are chances now that there will be bigger ARs, stronger in the future because of that added fuel.
I have heard some research from Professor Carlos Lobby from space research. He was with Professor Carlos Lobby. He studied atmospheric rivers coming from the Amazon and the importance of the atmospheric rivers for the Brazilian agriculture. And with deforestation, the atmospheric rivers are reducing the amount of water they are sent to the agricultural area. I was wondering if there are any kind of pilot researchers that can measure the amount of water vapor released to the atmosphere per hectare, for example. So, because this can be included in ecosystem services approach when you're developing recovering the greater landscape. So I was also wondering if you can develop these kind of projects, restoring the greater lands in areas that lack water resources, and you can, with your models,
A very interesting question about evapotranspiration, we call it, from plants into the atmosphere, and how that can be a source of water vapor that feeds atmospheric rivers locally, and then the atmospheric river transports that water vapor elsewhere that can contribute to precipitation there. Absolutely, I think that's a thing. I'm not an expert in the evapotranspiration, but it makes sense to me that the Amazon is a giant, lung essentially, which includes evaporating water into the air. It would be important to factor that in accurately into any prediction model, and one could, I suppose, with observations of that process, try to reduce the uncertainty in how much water vapor is getting into the atmosphere over the Amazon. But I imagine it's substantial.
Well, thank you very much to our three panelists, especially Dr. Gorodetska, who's, she can't hear me say that, but thank you for your time, and for Marty and Brad for being here and talking with us about this really important atmospheric phenomenon that has a lot of impact on everyday lives. So thank you again for our panelists, and thanks to all of you for coming today.